Though I really like the online implementation of the book, I always seem to just come to using the actual book here to visualize. The online version is good as well. But okay, so we started this last week, and we did a couple of lectures on it. Okay, just a very quick recap. Two groups, we're introducing this idea. It's a relationship amongst groups, isomorphisms. It's the formal way, the technical way of saying that two groups are equivalent to one another. Two groups, although they may have come from different mathematical contexts, although they might be defined as, at first look, being, well, defined on different objects, and the operations may be different operations, but as groups, just as a set of elements, and having an operation and the interrelationships that introduces amongst the elements, if they displaying the same group theory type structures, we want to say that two groups are equivalent, and that really essentially they're examples of the same underlying abstract group structure. Well, this is the idea of an isomorphism. So formally what it is, really what it is two groups are isomorphic if there exists a mapping between them. And this mapping between them is the mapping that realizes the equivalence, okay, that shows the same group theory structure going on in both of them. Okay, so two important things about the mapping. First of all, it has to be a bijection, meaning a one-to-one and onto function. Okay, so in particular, that means that the two sets have the same size. If they're finite sets, it means they have exactly the same number of elements. If they're infinite sets, the existence of a bijection between them is actually the definition of being of the same infinite size. Okay, so they are sets of the same size. And secondly is this, what's actually called the homomorphism property, because we'll be weakening the definition later to look at homomorphisms, which are maps which satisfy this property, which aren't necessarily bijections. Okay. So this is called the homomorphism property, and this is the second key thing. This is the property that says what's going on in a group theory sense in one group is the same as what's going on in the group theory sense in the other group. Okay. So in the definition here, G has an operation dot, H has an operation circle. So this product here, A dot B, is an operation going on in the domain group G. But phi of A circle phi of B, that's an operation going on in the group H between the elements phi of A and phi of B. Okay? And it's saying for every pair of elements A and B in the domain group G, that phi of the product A times B is the product of the phi's phi of A times phi of B. Okay? So whatever we see going on with the group operation in the group on the left, the domain group G, we're going to see exactly the same thing happening in the group H amongst the elements phi of A and phi of B. Let me look to a number of examples. In particular, it's helpful to think of the Hayley tables of these pairs of groups. Saying that the groups are isomorphic in this context is what you're saying is that if you take the Hayley table of one of them and you relabel the elements in a bijective way with the elements of the other group, if you can find a relabeling that also, as well as translating the elements from one group into the other group, you can always do that. If the groups have the same number of elements, you can always construct a bijection between them. But if you can find a bijection that at the same time brings the body of the table and maps the body of the table correctly across into the body of the other group table, then that's an isomorphism. Because when you think about what does it mean to take the body of the table in the group on the left and map it over to the body of this table, it means that every product over here, when you multiply 3 by 3, you get a certain element here. When you map that across, it's exactly the same as 5 times 5, and 3 gets mapped to 5. Okay. 3 times 3 is the product going on in this group. Phi of 3 equals 5. So 5 times 5, if that's going to give the same thing over, or that's going to give the mapping of whatever element is here, it gets mapped over to them. Okay. And then in the lecture on Friday, which a couple of you weren't at, and look, the recording of it is up there and the notes, we answered a few queries from earlier in the course, and then we focused on this theorem here, theorem 9.6. And this was establishing some kind of basic consequences of the definition of isomorphism. What this is a collection of group theoretic properties that we can see now are preserved by an isomorphism. So if there's any kind of group theory status that you can attach to G, if G is isomorphic to H, the same will hold true of H. Okay. So there's 5 statements here. Well, the first statement is just saying that isomorphism, it's actually a symmetric relation. So G is isomorphic to H is isomorphic to G. And really that's just about noticing that the inverse map, phi inverse, which does exist because phi is a bijection, the inverse map also satisfies the homomorphism property, so is also an isomorphism. Number 2, the groups are the same size. So that's a consequence of being isomorphic if the groups are finite. The existence of a bijection means they must have the same number of elements as a one-to-one bijection mapping. For infinite groups, this is actually, it kind of goes the other way around. The definition of the infinite groups having the same size is the existence of a bijection between them. The 3, 4, and 5 are classic examples of group theory property. If the groups are isomorphic, then the property has the same status in both groups. So if G is abelian, H must be abelian also. If G is cyclic, H must be cyclic. If G has a subgroup of order n, then H has a subgroup of order n. Now, the extension of 5 to every subgroup of G, really what it's saying is that the subgroup structure of G, the amount of subgroups it has, the sizes they have, we see exactly the same subgroup structure happening in H. Okay? Because every subgroup in G, the way we proved 5, when you look at the recording or the notes, is that we basically take the subgroup of G and map it across using the mapping phi, and phi of that subgroup will be a subgroup inside H. Okay? So as well as phi mapping the elements across between the 2 sets, it's also simultaneously mapping all the subgroups from one to the other. Okay? So whatever is going on with the subgroups in G, the same thing is going on with the subgroups in H. So 3, 4, and 5 can be taken in 2 ways. If we know the groups are isomorphic, then we know 3, 4, and 5. We know they have the same group theory structure. They can also be taken in another way. They can also be taken as tools to detect non-isomorphic pairs of groups. So if you find a pair of groups and one of them is abelian and the other one isn't, then we know they're not isomorphic. Because if they were, they would both have to be abelian. By the same reasoning, if you find 2 groups, one is cyclic, the other one isn't, they can't be isomorphic, okay? Because an isomorphism forces them to both be cyclic. And secondly, if you find some subgroup structure in one group and you can prove that it isn't present in the other group, if there's 2 different subgroups of order 5 in my first group, but my second subgroup has 3 different subgroups of order 5, well, that disparity can't exist if the groups are isomorphic. So that's like a proof that they're not isomorphic. Okay? So that's the 2 different ways we can take these results. As consequences, if we know the groups are isomorphic, but also as methods to detect non-isomorphic pairs. That's basically where we got to last time. Any questions about that, or queries, or things I could clarify about it? Is that okay? Yeah. Okay. Well, let's look at the other results then. The next, there's one that he kind of skips the proof of, so we'll go through that on paper. But the next few we'll just kind of read through from the text. These are, just more consequences of isomorphism. What we're starting to see with these results coming through here are, if you like, starting to classify the universe of groups itself. There's a broad kind of strategic endeavor in group theory, which has the goal of classifying all the groups, being able to understand the universe of groups, okay? All the possible groups that that direct. They're trying to describe them all and trying to have methods and tools so that if anyone plonks a group in front of you, you'll be able to slot that into your classification. Say, I know about this type of group. It's, belongs in this family. It's got this size. It's got this properties. Okay, that's the grand enterprise of kind of abstract group theory. And we see some in the initial, simplest parts of it here displayed in these results. First of all, Theorem 9.7, all cyclic groups of infinite order are isomorphic to Z. And by Z there, we mean the plain old integers under the operation of addition. Very familiar group, one you introduced to in your first days in primary school, taking the whole numbers, adding them together, subtracting them, using their additive inverses. So something you've known about all along, the group of Z, the integer Z under addition. What this is saying is that, well, every infinite cyclic group is actually equivalent to that, okay? So that's quite a powerful result. It's saying there isn't a whole universe of different types of infinite cyclic groups. Really, they're essentially all the same. They all really have the same group structure. So if anybody plunks down a pair of infinite cyclic groups in front of you, it should be possible to find an isomorphism between them. It should be possible to see that they're both equivalent groups. So let's look at the proof of it. It's quite a grand statement when you first see it. But then you start to see, well, what does it mean to be an infinite group, an infinite cyclic group? Well, being cyclic means you have a generator. Being cyclic means there exists some special element, at least one special element, such that every element in the group is equal to some power of that one element. Okay. Well, what can you do when you've got one element and you're building up powers of it? Well, let's call the element little g, or what's he call it here? A. So the A is a generator G. So if A is your generator, well, what elements can you make from it? Well, you can make the identity, A squared, A cubed, A4, A fifth, A6, A7, A8, etc., 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 etc. A inverse, A minus 2, the square of the inverse, A minus 3, cube of the inverse. Okay. Well, you can see the way you're building them up. You build them up by looking at powers, positive and negative of that element A. Then you're kind of just using the integers to label them, aren't you? Got A squared, A cubed, A4, they're the positive integers. Got the negative integers, A inverse, A to the power minus 2, which is the square of the inverse, etc. So you see, when you just start to look at the elements in this infinite cyclic group, there's a natural way to label them with the integers. That is exactly the mapping phi. So what he's doing here is just spelling that out. So let G be a cyclic group of infinite order. Suppose that A is its generator. So everything in G is some power of A. So then we can construct our mapping. So he constructs the mapping in the direction from the integers to G. Just using this labeling that I was just counting out in my fingers there. We send the integer n to the element A to the power n. So there's a couple of things we will have to show about this map phi. We'll have to show that it's a bijection. We'll have to show it satisfies the homomorphism. So the first thing to do is to show it satisfies the homomorphism property. The homomorphism property is the statement on the left. This is the product of the two integers n. Now, by product, we mean taking the two integers and combining them using the group operation. When we just talk about the group Z on its own, we mean the operation being addition. So the product here is what we know more usually as m plus n, just the sum of the two integers. What is phi of m plus n? It's a to the power m plus n. That's the rule for phi. But then using a property of indices, the meaning of a to the power m plus n, we can easily see that as a to the power m times a to the power n. And that is phi of n times phi of n. Okay. So this group product here is taking place in the group G. You got an element of G, a to the m, multiplied by another element, a to the m. Okay. And that's the homomorphism property. So the only other thing to do is to prove that it is a bijection. Onto is clear. because by definition, if it's cyclic, everything is of the form a to some power. So it's clearly onto, because whatever the power is, phi will send that integer to that element. The only thing is to look at the injective. And the way he does that, he proves this kind of by contradiction in a way. So it says, suppose m and n are two elements, two integers, where m is different from n. That's not really, well, there's a contradiction, yeah. So he's assuming that m is strictly bigger than n. One of them must be bigger, so let's just say m is the bigger one. We have to show that a to the power m is not the same as a to the power n. So he does this by proof by contradiction. So suppose, on the contrary, that a to the power m is equal to a to the power n. Multiply both sides by a to the power minus n, the inverse of a to the n. So you got the identity on the right and a to the power m minus n on the left. Now, by assumption, n is different to n, and m minus n is a positive number. So we seem to be looking at a positive power of a, which is the identity. But that would say that a is finite order. The element is finite order. But it doesn't. It's a generator of an infinite cyclic group, so it can't have finite order. That's a contradiction. Okay? Contradicts the fact that it's an infinite order. So therefore, this assumption can't be true, so it must be true that a to the m is different from a to the n. So that shows the map is injective. If you've got different arguments, m and n, they get sent to different elements. Okay. Theorem 9.8 addresses finite cyclic groups. If a cyclic group G has finite order n, then G is isomorphic to Zn. And by Zn, we mean the integers modulo n under addition modulo n. Yeah. Well, it's still the same idea. It's the same idea, sending the integer to the power a to the k. He's delegating the proof for that to one of the exercises, but it's really just applying the same ideas as in the previous one. Okay? So those two results together are nice. It's saying, you know, really, cyclic groups are captured by the idea of the group of integers or the idea of the group of the integers modulo some n. Those are the cyclic groups, and every other cyclic group is going to be equivalent to one of those. Corollary 9.9 says, well, if you've got a group of order p, where p is a prime number, well, there isn't a whole lot of possibilities, really. There's only really one possibility for that. It has to be isomorphic to the group zp, the integers under addition modulo p. Okay. That's from a previous corollary. The previous corollary was saying if the group is prime order, it has to be cyclic. That was proved because we've showed that the order of any element has to be a divisor of the order of the group. But prime numbers don't have divisors except 1 and p. The identity is the only element of order 1, so every other element in the group must have order p. So every element in the group, apart from the identity, is a generator of the group. So it's cyclic. It's cyclic of order whatever. By the previous theorem, it's isomorphic to the integers modulo that size. Is that okay? Any questions about those results? Okay, the next one to look at is Theorem 9.10. And this just kind of puts a bit of context on the idea of this isomorphism relation between groups. And that says that it's isomorphism is an equivalence relation. Well, how do we prove this? Well, we just need to remember an equivalence relation. An equivalence relation is a relation that is symmetric reflexive, and transitive. Let's just take these one by one. So symmetric, if G is isomorphic to H, well, we've already shown in Theorem 9.6 theorem 9.6, H is isomorphic to G. So if the isomorphism relation goes one way, it automatically comes back the other way. Okay. So we can talk loosely about pairs of groups being isomorphic. The isomorphism itself is a mapping from one group to the other one. So yeah, so the isomorphism has a direction. But now we know that the relation of being isomorphic goes both ways. So we can speak loosely as it just applies to pairs of groups. So that's the symmetry property. The reflexive property says that every group is isomorphic to itself. Well, that kind of seems obvious. I mean, we're introducing this idea as an equivalent, you know, as being able to say that groups are equivalent. Obviously, everything is equivalent to itself. But if we wanted to just prove it formally, how do we prove something is isomorphic to itself? Well, we have to construct the isomorphism. So what is the bijective mapping from G, any group G to itself, which is an isomorphism? Let's see. The identity map has to be that. That's the obvious mapping from any group to itself. And that's going to, so clearly the identity map, let's just call it ID from G to G. So that's the map defined quite boringly by ID applied to little g, just equal to G. Very boring map. No, you know, it just sends everything to itself. That's clearly an isomorphism. It's bijective, and is ID applied to a product going to be the product of the IDs? Well, yeah, because it doesn't change anything at all. But more interestingly, and this is something which will come up later on, more interestingly, are non-identity maps. Non-identity maps from G to itself. So that's more interesting. Other ways of mapping a group to itself, which are isomorphisms. So bijective maps from a group to itself, which satisfy the homomorphism property. These are called automorphisms. Automorphisms. And that's quite an interesting topic. That gives an interesting way to study a group. An interesting aspect of a group will be all the different ways that it can be isomorphic to itself. All the ways of relabeling itself that makes it a group equivalent to itself. Kind of a bit of a mind-bending idea. But so some groups have lots of automorphisms. Some groups are very limited in the amount of automorphisms that they have. So that's interesting. Okay, but we won't chase that further for now. So that's the reflexive property of the isomorphism relation. Every group is isomorphic to itself. And now finally, transitive. So for transitive, we should assume G is isomorphic to H, and H is isomorphic to K. Well, what does the transitive property mean? The transitive property means that G is isomorphic to K. The isomorphism kind of travels through H. We want to show that G is isomorphic to K. Well, if we want to show G is isomorphic to K, we have to construct an isomorphism between them. We have to identify what the mapping is from G to K. Where is it going to come from? Well, it's going to come from gluing together the mapping from G to H with the mapping H to K. That's how we're going to get from G to K. We're going to travel through H. Of course, gluing together isn't the correct term. What I'm referring to there is composing the maps. Okay? So let phi1 from G to H and phi2 from H to K be the isomorphic mappings, isomorphisms, and claim phi2 after phi1, so that's a mapping from G through the intermediate H all the way to K, composing those mappings. The claim is that that is an isomorphism. I mean, it's the obvious one, isn't it? We know G is isomorphic to H, we know H is isomorphic to K. How are we going to show G is isomorphic to K? Well, we're going to stick those two mappings together or compose. Phi2 after phi1 is a bijection. Since phi1 and phi2 are. That's not a group theory property, that's just a property of one-to-one and on-two maps. When you compose two together, the result is one-to-one and on-two. Maybe what is interesting to prove is the isomorphism property. Okay? Sorry, the homomorphism property. So if we let A and B be two elements of G, what we want to look at is phi2 composed with phi1, that map applied to the product AB. Well, this is equal to, well, by definition of composition of maps, this is phi2 of phi1 of the product AB. This is the definition of what we mean by composing maps. But phi1 is an isomorphism, so phi1 of A times B is equal to phi1 of A times phi1 of B. That's true because phi1 is an isomorphism. But now we see phi2 applied to, well, what are these here? This is an element, so phi1 of A, where's phi1 of A? Phi1 of A is an element inside H. Okay, and so is phi1 of B. A and B are in G, so you map them using phi1, you have two elements of H. Well, here we have two elements of H multiplied together, taking place in H, and then I apply the map phi2. So that sends this single element here, which is phi1A times phi1B, that single element of H, it sends it into K. But phi2 is an isomorphism. So that's equal to phi2 of phi1 of A multiplied by phi2 of phi1 of B. The justification there is since phi1 an isomorphism, and that's true since phi2 an isomorphism. But finally, what we can re-express these two. Phi2 of phi1 of A, that's clearly the composition map phi2 after phi1 applied to A, and phi2 of phi1 of B is clearly the isomorphism map phi2 after phi1 applied to B. Maybe stick a pair of square brackets there just to simply emphasize, singling that out as a single object, single element of K. And this thing here in the square brackets is the other single element of K. And from the start to the finish there, that is the homomorphism property for the composite map, phi2 after phi1. You've got phi2 after phi1 at the product equal to the product of the individual images of phi2 after phi1, applied to A and applied to B. Okay? So this is the homomorphism property. This is the homomorphism property for phi2. So it is transitive. Okay. G is isomorphic to H and H is isomorphic to K. The relation does travel through K, and it says G is isomorphic to K. So G is isomorphic to K. G is isomorphic to K is. Okay, so isomorphism satisfies the three properties of being an equivalence relation. So we're justified in using, that puts it in this established context of an equivalence relation. Okay, so we're looking at the universe of groups, and we're splitting up, we're clumping together the different groups. We clump groups together if they're isomorphic. So we're introducing this relation. Any questions about that? Okay. So the other remaining thing to look at is Hayley's theorem. So Hayley's theorem is, well, we introduced it before. We were given a clue to it in one of the exercises in the permutation groups chapter. So the bold statement itself is this very, very, in one sense, it's an exceedingly strong statement. Every group is isomorphic to a group of permutations. That seems amazingly strong because we introduced permutations as a kind of important example of an important family of examples of groups. But they were only one family of groups, and we looked at dihedral groups, we looked at the integer groups, the modular integers, we looked at we referred to other symmetry groups of geometrical objects, three-dimensional rotation groups, and so on, with groups of real numbers and that. But suddenly it's saying, well, actually, if you understand groups of permutations, you understand every group. Every group is isomorphic to some group, to a group of permutations. Now, one good way of getting a handle on this, or seeing an example of this, is to look at an example of a Hayley table or two. So if we, that's not in there, if we hop into Sage, sorry. I just want to, now he shows an example of a Hayley table in the book, but it's only of Z3, it's a little bit small. So I just wanted to, see a proper example. Just a more decently sized group. What's our favorite group at the moment? And we won't choose a permutation group because that's already obviously isomorphic to a group of permutations. So let's take some dihedral group. I know they're implemented as permutation groups in Sage, but by definition, as a group of symmetries of a certain geometrical object, a regular polygon, the dihedral groups are different to permutation groups. So let's take one, say, the dihedral group D10. So this is the group of symmetries of a 10-sided regular polygon. And we'll look at the Hayley table. Now, by definition, or by default, it just uses the first 10 letters of our alphabet as labels for these elements. So I can't tell just by looking at these pictures, which are half of them are rotations, half of them are reflections. But we just got these 20 elements labeled A through T. There's the Hayley table for them. But what do we say? What information are we picking out here? When you look at each row of the Hayley table let's say, look at this row H here. We see again all the 20 letters A through T. You look at another row, row K, we see all the letters A through T in some mixed up way. Okay. Here are the original set of letters A through T. In each row, what we see is a different permutation of them. Okay. So there's this just from the Hayley table itself, there's this natural association with each element of the group here. So here we have all the elements of the group, A through T. And each element is naturally associated to, because it's just right beside, a permutation of all of the group elements. Okay. So here's an element F. Here is a permutation, when you look across the row, of all the elements A through T. And it's easy to see how it's generated. The permutation is generated. The image of A is F times A. The image of B is F times B. It's just how the Hayley table is constructed. Okay. So rather than thinking of the 20 elements of D10, there's 10 rotations there, 10 reflections. Instead, we can think of the 20 permutations of the characters A through T. So that's the mapping from the elements of the dihedral group D20 across to this collection of 20 permutations of the 20 symbols A through T. Okay. That's essentially the Hayley isomorphism that we're talking about in Hayley's theorem. Okay. So he introduces that idea in example 9.11 there at the bottom of page 155 with Z3, but it's going to be a bit more satisfying when you see it on a bigger group, like we just looked at. Okay, so let's look at the proof of Hayley's theorem. That's it all there on the screen. So the claim is every group is isomorphic to a group of permutations. So he starts off, let's G be a group. Now he says we must find a group of permutations, and he calls that G bar, G with the overline, so you can read that in English as G bar. G bar that is isomorphic to G. For any little g in G, define this function lambda sub G from G to G by lambda sub G times A is equal to G times A. Okay, what's he talking about there? When you first see that, it seems like a big load of gobbledygook, but when you start to parse it, think carefully about what he's saying there. All he's saying there is that for each element from the group, we define this permutation, lambda G. He goes on to confirm that lambda sub G is a permutation. And the definition of the permutation is, well, to define a permutation, it's a mapping from this set to itself. So you have to define it. So what is lambda G applied to A? It's simply G times A. But that is exactly what I was just pointing out to you, just showing you with our Hayley table. So here's our little g, so to speak, of D10. This row here, when you match these original arguments, A through T, with these images here, G, F, D, C, G, J, B, etc., each of these is G times whatever the element is. So this thing here, C, is G times D. Okay. So we're actually seeing here all the images strung out in that row there of the mapping lambda G. Lambda G applied to D10. And here we see lambda H applied to D10. See all the images. So that's the permutation. So the proof then is just to prove, well, firstly, prove that lambda G is a permutation. So to prove that, you just have to prove that it's one-to-one and onto. That just comes naturally from the fact that G is a group. So to prove it's one-to-one, suppose you've got two elements A and B that have the same image under lambda G. But that means G times A, which is lambda G, must be the same as G times B. But you're in a group, so you can simply cancel the G from both sides. Sides on the left by G inverse, the G's drop off, and you're left with A equals B. So that shows that lambda is a one-to-one mapping. Secondly, you must show that lambda G is onto. So to show it's onto, you take an arbitrary element from G, and you ask, is there an element little b such that lambda maps b to A? Well, there is. Since you're going to multiply b by G on the left, the correct element to use is G inverse A. When you multiply that element, G inverse A, on the left by G, the G and G inverse cancel, and you're just left with A. So lambda is onto. So it is a permutation. That's a permutation is just another word for, sorry, a permutation of a certain set is just another word for a bijective mapping of the set to itself. So G bar is a collection of permutations. G bar is just the set of all these mappings, lambda G. And then you just have to prove that it's an isomorphism. So you have to show that this mapping, so I guess the mapping, the isomorphism itself, you could, you don't want to confuse, I don't think he names it here. But yeah, you could say the isomorphism itself, the isomorphism from G to G bar is this mapping lambda. And lambda sends an element little g to the permutation lambda sub G. Okay, so that's the actual isomorphism. Or sorry, he does define that at the bottom as phi. So this the rest of the argument there is simply proving that G bar is a group. Okay, we've already proved it's a set of permutations. You just have to prove it's a group. You have to show that the identity element is present. The identity element is present because the identity element corresponds to the permutation lambda sub E. So you're multiplying everything by E, but of course that leaves it unchanged. So lambda sub E is the identity map. It sends A to A for any A. It's closed because if you compose two maps, remember the group operation, and because it's a group of functions, it's a set of functions, the group operation you're going to be using is composition. You compose two of these lambda maps. Well, the effect that has on A is to multiply A by G times H. Because you're in a group, so everything's associative. We don't have to put in the brackets. So we can consider this as the element GH times A. But of course, that is just the effect of the map lambda sub GH. And G times H is just one of the other elements of the group, of the original group G. So this mapping, lambda sub GH, will be present in G bar, because G bar contains all the lambdas corresponding to elements of the group G. So G bar is certainly closed. You have to show it has inverses, and the inverses are naturally the inverse of the map. The inverse of the permutation lambda G is the permutation lambda G inverse, the one constructed by the element G inverse. So it's closed, it has the identity element, it has all the inverses. Does he prove? Well, he doesn't need to prove associativity because the group operation we're talking about here is composition of functions, and we already know that to be associative. Composition of functions is kind of universally associative, no matter what the functions are. If they can be composed, that composition is associative. So we know G bar is a group. So then, finally, then we just need to say that yes, we've already proved the, we've already established. Or did we establish the isomorphism property? No, the isomorphism property is confirmed here. So this mapping is phi. Phi is the mapping from G to G bar itself, where we send the element little g to the permutation lambda G. Let me just observe that it satisfies the homomorphism property. And that's just this thing which was already observed up here, that the permutation corresponding to the element G times H is just the composition of the permutations, the one corresponding to G composed with the one corresponding to H. Okay, so therefore it satisfies the homomorphism property. So that establishes Cayley's theorem. It's quite it's a kind of a surprising thing, as I said, to suddenly meet, because up to now we've kind of presented the permutations as like one important class of groups, but they're by no means all the groups. There's lots of other different types of groups. But now we're suddenly saying any group at all is isomorphic to a group of permutations. So, I mean, how should you think about this? Maybe the naive way to think about it is that, oh, this suddenly simplifies everything. Because now, if we want to understand the universe of groups, all we need to do is understand the universe of permutation groups. It suddenly makes everything seem a lot easier. Permutation groups are just these simple little symbols we've been writing down, you know, the cycle 1, 2, 3, 4, yeah, nothing too wacky or complicated. But that's kind of, that's not the correct way to think about it. The correct way, it isn't really saying that the study of groups is suddenly simplified. What it's really saying is permutation groups, which we thought were just one of the examples of groups and, you know, not too hard to understand. What it's really saying is permutation groups are really, really complicated. They're as complicated as the whole universe of groups. Yeah. Because any group whatsoever, you'll be able to, you know, hypothetically, or no, that's not the correct word. In principle, you can construct a group of permutations that is isomorphic to that other group. Okay, so the universe of permutation groups contains within it all of the structure of the total universe of groups. Think about it like a giant fractal. Whatever structure there is in the universe of groups is already present in the universe of permutation groups. And it's not really, it doesn't really simplify everything. Well, it does in a sense. You can just study permutation groups, but you're not eliminating any complexity. Cayley's theorem says permutation groups are as complicated as the whole universe of groups. Okay? But this kind of, what we've been seeing in some of the SAGE examples up to now is whatever group we get SAGE to manipulate, it all, you know, the dihedral groups, you know, it seems to represent everything as permutation groups. Well, you can kind of see the reason for that now. It's really permutation groups capture everything that there is going on about groups in a sense. Okay, so it's a nice result to think about. A bit more terminology presented here. This isomorphism from a group to that permutation group is known as the left regular representation of G. Left regular, well, you can kind of see you could set up this whole machinery where instead of multiplying the element A by G on the left, I mean, why are we multiplying A by G on the left? Well, just because we decided to. You could equally well run this whole argument by instead considering the permutation where you multiply A on the right by G. That would be the right regular representation. What that would be equivalent to is instead, you see here I focused on the rows as representing the permutations. That would be instead focusing on the columns. Equally well, when you look down a column of the Cayley table, in the body of the Cayley table, what you see is a permutation of the row indices. Down this E column here, I just see the letters A through T rearranged, permuted. And for some groups, especially for non-commutative groups, for non-abelian groups, that representation might be a different representation, different isomorphism. Okay, we've got to finish there now for today. So we'll finish off this chapter 9 on Friday. We'll look, there's a couple of topics to look at, the direct